Here I have an HTTP-based Go microservice, and I'm going to modify it, containerize it, and then deploy it to our EKS Kubernetes cluster to show how FizzBuzz Pro component deployment lifecycle works end-to-end. Let's start with this Docker file, which is a manifest file that will help create the container image for this service. And in this Docker file, we are using multi-stage builds. And you can check out the notes on this video's webpage for more information about how this multi-stage build works. So let's analyze this Docker file line by line. We are using a Go-based image in our build environment, and we'll be using a minimal Scratch image as our final artifact that we are going to deploy to the container registry. After setting the build base image, then we are installing Git on top of our base image. After that, we create an unprivileged user to secure the container image that we are going to generate eventually. And then we copy this .netrc file to our build image so that we can fetch private Git repositories as Go dependencies into our build environment. And again, check out the notes on this video's webpage about the contents of this .netrc file and also how you can set up a .netrc file for yourself. But essentially, this file is here so that we can fetch private Git repositories that we have. Then we set a working directory. We copy our Go module files to this working directory and then download the module dependencies that we need. And after that, we copy all the source code that we have here into the build container. Then we build our application with this command, and this app binary executes this command /main go as the entry point of our application. And as the second stage of the build, we create another image from scratch so that we don't have all the baggage that we had in this build image. We'll copy only the stuff that we need from the build image to this scratch image, nothing else. So what do we copy? We copy the unprivileged user and group files from the build container to our final image so that we can assume that user in the container for security reasons. And then we copy the certificate authority files. And finally, we copy our binary from the builder image to our final image. And after that, we switch our user from root to this unprivileged user, which will make our container more secure. After that, we expose the port that our Go microservice is serving and set this app binary as our entry point. And to build and publish this image, we have this hex/build.sh, and in the build.sh file, we get the image name, the tag that we are going to publish, and the repository name that we are going to publish to from our environment variables. And for the curious out there, let's see how these environment variables look like. So this ECR repo is the URL of our Amazon Elastic Container Registry, or ECR repository. And you can check the links on this video's webpage again for how to set up an ECR repo. But here I will assume that we already have one set up and is ready to be used. And the tag is a regular good old semantically versioned tag name. And the image name here is the name of the image that we are going to push. And before I continue with the file, I'll slightly change this command /main go main entry point so that we can verify that we have actually deployed our service. I'll add a dummy log line here so that we can check the logs and verify that we have deployed this service without any problem to our Kubernetes cluster. So now let's cross our fingers and run this build script, shall we? Well, it went well to a certain point, but then it said that I need to authenticate to ECR, which I have a nifty alias to do it, so I'll share that command for you to see how it looks like. And when I call this login ECR alias, I successfully authenticate with the Elastic Container Registry. And now I think if I run the build script again, I'll be able to successfully publish my image to the ECR registry. So let's run the build script and test it out. And now I get a warning that I already have an image with this tag, because silly me, I forgot to source my zprofile file. Although I bumped up the tag name, so the tag name is different than this one, but I haven't sourced the profile file, so it's using the old tag name. So let's source zprofile, which will update the tag name from 0.0.14 to 0.0.15, and then we'll try building again. And now we have successfully pushed the image to ECR, and from the console output, we can say that everything is awesome, isn't it? So shall I believe the output? Probably, but I'll still double check it in the ECR web UI to make sure that we have successfully published this image to the Elastic Container Registry. But before that, let me show you the pods that we have in the production system. And to get the list of pods that we have, I'll do a kubectl get pod, and it will list the pods that we have. So these are the pods that are active on the production system as of now. And as you see, there is this crypto pod that is linked to the project that we just modified. And similarly, when I list deployments by doing a kubectl get deployment, I can see a deployment for crypto, which essentially manages this CryptoPod. And I want to delete this deployment, which will cascade and delete this pod as well. And for the record, in a production application, you'd probably want to do a rolling update deployment strategy instead of flat out deleting the deployment, which will delete the entire pod set, which will make the application unusable. On the other hand, if you do a rolling upgrade, the application will be online at all times. So for a production application where high availability is important, updating your deployment to a new image is a better strategy than deleting the deployment entirely. But since nobody is using this system right now, we can safely delete this deployment. So let's do it. And to do that, we'll do kubectl delete deployment crypto, which will delete the crypto deployment and all of the pods that this crypto deployment is managing. And after deleting the deployment, when we check for pods using kubectl get pod, you see that the CryptoPod is no longer available. And when we check for deployments via kubectl get deployment, you'll see that the crypto deployment is gone as well. So let's see some of the other manifests in our deployment setup. For example, this is our ingress manifest, which effectively links an Amazon Web Services application load balancer to our cluster to enable incoming traffic. And I'm going to talk about this ingress setup in a follow-up video in more detail, so I'll just skip that for now. And this is a config map that all of our microservice pods refer to. Now it only has a single setting, but in the future we might add more configuration options to it. And this services folder contains a folder for each microservice that our application has. And each service folder in itself has a set of manifests that are associated with that service inside that folder. And since we are deploying the crypto service and we are going to deploy this crypto deployment, I'll just look into these crypto microservice related manifests files. But the other service manifests are quite similar as well. So just checking this crypto will give an adequate idea about how the other services behave as well. And this is the config map that our crypto microservice references. It has a bunch of data that we are going to link as environment variables in this deployment manifest. And this is our service manifest, which creates a DNS entry for this service in our cluster and acts as a load balancer for the microservice pods that our deployment is managing. And here port 80 is the port that the service exposes to the outside world, and the port 9001, if you remember, is the port that our Go microservice is using. So the service listens at port 80 and reverse proxies traffic to our microservice pod that is listening at port 9001. So if that's a little confusing right now, what I mean will be clearer when we look at this crypto deployment YAML. So let's open that file as well. So we have a deployment named crypto, and we are referencing this image to provision the container that our pods are going to use. And since we have a replica count of 1, we are going to have a single pod that will have a single container in it, but we can always increase this replica count to load balance against more than one pod. And as you see here, we are binding the values of our config map as environment variables to our pod using this env template section. And similarly, we bind more sensitive environment variables by using secrets instead of config maps, but the structure is almost identical otherwise. And to use the new image, we need to bump up the version from 0.0.14 to 0.0.15 that we just published to the registry. But before that, let me navigate to the ECR repository's web UI and verify that we have the image in the repository. And when I check the web UI, we can see that we have the image in the repo with the tag name 0.0.15. So far so good. So I bumped up the image tag in this deployment manifest from 0.0.14 to 0.0.15. So let's apply this deployment and see what happens. And to apply the deployment, we'll do a kubectl apply -f crypto deployment.yaml. And that's pretty much it actually. Calling this kubectl apply command will create the deployment with a single pod that the deployment manages. So when I list all of the services by doing a kubectl get service, I see that we have a service named crypto as well. This service is acting as a load balancer or the front-facing proxy behind the CryptoPod that we have just created when we applied the deployment manifest. But since this crypto service is not exposed to the outside world with our ingress controller, we can only reach it from within the cluster. So to verify that we can reach the service, I'm going to use a Kubernetes job that I have created a while ago. Let's see the manifest descriptor of the job first. Well, this job creates a single Nikolaka netshoot container in a pod, and it keeps the container alive long enough so that we can shell into the pod and inspect the cluster from within that container. And Nikolaka netshoot is a popular image which includes a bunch of network diagnostic utilities. So it's typically used to explore the pod network and the DNS and other network related issues from within the cluster. So we'll use it to do similar things. I'll first list the existing jobs that we have by kubectl get job, and then delete this completed job named BusyBox, and then create a new job by doing a kubectl apply -f busybox.yaml, and that will create the pod that we can attach to. So when I list the pods in the cluster by doing a kubectl get pod, we see that this busybox pod is live and kicking. So I'll attach to it by doing a kubectl exec-it pod name --bin bash. And now we are inside the pod. So we have visibility into the Kubernetes cluster, and we can curl the crypto service and see that it's returning a JSON response to our health and also liveness API request at these healthz and readyz endpoints. And also when we ping to this crypto service, we see that it has an IP and also it has a local DNS name. And we can even verify that we can connect to our crypto service on port 80 by opening a telnet session to it through telnet crypto 80. So all in all, we appear to have deployed crypto service to our cluster again. But is it the new container image that we have deployed? Do we have the new code that we built, bundled, and pushed to the registry? To verify that our code on the container is up to date, I'm going to navigate to Papertrail, which FizzBuzz Pro microservices are using as a log aggregator endpoint. And to see where to look at, first I'll do a kubectl getpo to check the name of this new CryptoPod. So the name of the CryptoPod ends with QNJ8L. So let's dig into this system in Papertrail that also ends with QNJ8L. And voila, we can see the dummy log line that we added into the source code at the very beginning of this video, which verifies that we are using the recent image and the recent code. And that concludes this demo. I'll cover parts of this system in more depth and detail in the upcoming videos. But for now, as far as building an image and deploying it to the cluster goes, that's all there is to it. And until the next video, may the source be with you.